Section 230.80 of the National Electrical Code requires that the service be large enough to provide the total load calculated in accordance with Article 220. In this scenario, the calculated load is 173 amps, but the owner plans to use 3 meters of 200 amp meter for the apartment and 2 100 amp meters for the garage and office respectively. While the code permits multiple meters, the service size must be determined by the total calculated load. Consequently, a 200 amp service is insufficient. To determine the appropriate service size, utilize the following formula: service size equals calculated load plus demand factor times 1.25. Assuming a demand factor of 0.75, the service size calculation is as follows: service size equals 173 amps plus 0.75 times 173 amps times 1.25, resulting in approximately 379.31 amps. Therefore, a minimum 400 amp service is required for this building. It is crucial to consider that specific types of loads, such as electric vehicle charging stations, may necessitate a larger service size. Consultation with the local utility company or a licensed electrician is recommended to determine the appropriate service size for the specific installation. Let's delve deeper into the concepts and calculations involved in sizing an electrical service for a multifamily building, ensuring compliance with the National Electrical Code and meeting the demands of the connected load. Firstly, understanding the components of the load calculation is essential. The calculated load represents the total amperage required by all the electrical equipment and appliances within the building. This includes lighting, receptacles, heating, ventilation, air conditioning, and any other electrical loads. Article 220 of the NEC provides detailed guidelines on how to calculate these loads, taking into account factors such as square footage, appliance ratings, and occupancy type. Secondly, the demand factor is a crucial element in determining the service size. The demand factor recognizes that not all electrical loads will be operating at their maximum capacity simultaneously. It is a multiplier less than 1 that is applied to the calculated load to account for this diversity. The specific demand factors used will depend on the type of loads and the occupancy of the building, as outlined in Article 220 of the NEC. Thirdly, the 1.25 factor in the formula represents the requirement to size the service conductors and overcurrent protection devices at 125% of the continuous load. This is intended to prevent overheating and ensure the reliability of the electrical system. Continuous loads are defined as loads that operate for 3 hours or more at a time. Examples of continuous loads include lighting in commercial buildings and heating systems. Next, consider the impact of electric vehicle charging stations on the service size. Electric vehicle charging stations can draw significant amounts of power, especially level 2 chargers and DC fast chargers. The NEC requires that the service be sized to accommodate the maximum potential load of these charging stations. This may involve adding the full rated amperage of the charging stations to the calculated load, or applying a demand factor based on the number of charging stations and their expected usage. Moreover, the presence of multiple meters can complicate the service sizing process. While the code allows for multiple meters, it is important to ensure that the service is large enough to accommodate the total load of all the metered areas. This may involve coordinating with the utility company to determine the appropriate service size and metering configuration. Additionally, the physical installation of the service conductors and equipment must comply with the requirements of the NEC. This includes proper grounding, bonding, and overcurrent protection. The service conductors must be sized to carry the calculated load, and the overcurrent protection devices must be selected to protect the conductors from overload and short-circuit conditions. Furthermore, local amendments to the NEC may affect the service sizing requirements. It is important to check with the local building department or electrical inspector to determine if there are any additional requirements or restrictions. In addition, coordination with the utility company is essential throughout the service sizing process. The utility company will typically have specific requirements for the service entrance location, metering equipment, and grounding. They may also require a load letter or other documentation to verify the calculated load. In summary, sizing an electrical service for a multifamily building requires careful consideration of the calculated load, demand factors, continuous loads, electric vehicle charging stations, multiple meters, and local code requirements. By following the guidelines of the NEC and consulting with qualified professionals, it is possible to ensure that the service is adequately sized to meet the needs of the building and its occupant. Let's examine the step-by-step process of calculating the service size, emphasizing the practical application of the NEC guidelines. Firstly, begin with a detailed load calculation for each occupancy unit and common area within the building. This involves identifying all electrical loads, including lighting, receptacles, appliances, HVAC systems, and any other equipment that will be connected to the electrical system. For lighting loads, use the NEC prescribed watts per square foot values based on the occupancy type. For receptacles, use the NEC minimum allowance for general use receptacles. For appliances and HVAC systems, use the nameplate ratings to determine the amperage. Secondly, apply demand factors to the calculated loads. Consult Article 220 of the NEC for the appropriate demand factors based on the type of loads and the number of units. For example, demand factors for dwelling units typically decrease as the number of units increases. Demand factors for HVAC systems may also vary depending on the climate and the type of system. Thirdly, determine the total calculated load for the building by summing up the individual loads after applying the appropriate demand factors. This will give you the total amperage that the service must be able to handle. Fourthly, account for any continuous loads. If there are any loads that will operate for 3 hours or more at a time, such as lighting in common areas or heating systems, increase the amperage of those loads by 25%. This is to ensure that the service conductors and overcurrent protection devices are adequately sized to handle the continuous load. Fifthly, consider the impact of electric vehicle charging stations. If the building will have electric vehicle charging stations, add the maximum potential load of those charging stations to the total calculated load. The NEC provides specific requirements for sizing the service to accommodate electric vehicle charging stations depending on the number of charging stations and their charging capacity. Sixthly, if the building has multiple meters, ensure that the service is large enough to accommodate the total load of all the metered areas. This may involve coordinating with the utility company to determine the appropriate service size and metering configuration. Seventhly, apply the 1.25 factor to the total calculated load, including any continuous loads and electric vehicle charging station loads. This will give you the minimum required service size in amps. Eighthly, select the appropriate service conductors and overcurrent protection devices based on the calculated service size. The service conductors must be sized to carry the calculated load, and the overcurrent protection devices must be selected to protect the conductors from overload and short-circuit conditions. Consult the NEC for the appropriate conductor sizes and overcurrent protection device ratings. Ninthly, verify that the service entrance equipment and grounding system comply with the requirements of the NEC. This includes ensuring that the service entrance equipment is properly rated for the voltage and amperage of the service, and that the grounding system is properly installed to provide a safe path for fault current. Tenthly, coordinate with the local utility company to determine the requirements for the service entrance location, metering equipment, and grounding. The utility company may have specific requirements that must be met in order to connect the building to their electrical grid. By following these steps, you can ensure that the electrical service for a multifamily building is properly sized to meet the needs of the building and its occupants, while also complying with the requirements of the National Electrical Code. Let's address some common challenges and considerations that arise when sizing electrical services for multifamily buildings. One common challenge is accurately estimating the demand factors for different types of loads. The NEC provides guidance on demand factors, but it is important to consider the specific characteristics of the building and its occupants when selecting the appropriate demand factors. For example, if the building has a high proportion of elderly residents, the demand factors for heating and cooling may be higher than those for a building with a younger population. Another challenge is accounting for future expansion or changes in occupancy. It is important to consider the potential for future additions or renovations that may increase the electrical load. It is also important to consider the possibility that the occupancy of the building may change over time, which could also affect the electrical load. To address these challenges, it is often advisable to oversize the electrical service to provide some headroom for future growth. This can help to avoid the need for costly upgrades in the future. Another consideration is the impact of energy efficiency measures on the electrical load. Energy-efficient appliances, lighting, and HVAC systems can significantly reduce the electrical load of a building. However, it is important to accurately account for these energy efficiency measures when calculating the service size. Using overly conservative demand factors can result in an oversized service, which can increase the cost of the electrical installation. Additionally, the location of the electrical service can also be a consideration. The service entrance should be located in a place that is easily accessible for maintenance and repairs. It should also be located in a place that is protected from the elements. In some cases, it may be necessary to install multiple service entrances to serve different parts of the building. This can be more costly than installing a single service entrance, but it can provide greater flexibility and reliability. Moreover, the type of electrical service can also be a consideration. The most common types of electrical service are single-phase and three-phase. Single-phase service is typically used for smaller buildings, while three-phase service is typically used for larger buildings. Three-phase service is more efficient than single-phase service, but it also requires more complex electrical equipment. The choice between single-phase and three-phase service will depend on the size of the building and the electrical load. Furthermore, the grounding system is an essential part of the electrical service. The grounding system provides a safe path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. The grounding system must be properly installed and maintained to ensure that it is effective. In addition, the overcurrent protection devices are also an essential part of the electrical service. The overcurrent protection devices, such as circuit breakers and fuses, protect the electrical system from overload and short-circuit conditions. The overcurrent protection devices must be properly sized and installed to ensure that they will trip in the event of a fault. By carefully considering these challenges and considerations, it is possible to design an electrical service that is safe, reliable, and efficient. It is always advisable to consult with a qualified electrical engineer or electrician to ensure that the electrical service is properly sized and installed. Now, let's walk through a more detailed example to illustrate the application of these concepts. Suppose you are sizing an electrical service for a 3-story apartment building with 12 dwelling units. Each dwelling unit is 1,000 square feet and has an electric range, a refrigerator, a dishwasher, a clothes washer, and an electric dryer. The building also has a common area with lighting and receptacles. Firstly, calculate the general lighting load for each dwelling unit. According to the NEC, the general lighting load for dwelling units is 3 watts per square foot. Therefore, the general lighting load for each dwelling unit is 3 watts per square foot times 1,000 square feet equals 3,000 watts. Secondly, calculate the small appliance load for each dwelling unit. According to the NEC, each dwelling unit must have at least 2 20-amp small appliance circuits. Therefore, the small appliance load for each dwelling unit is 2 circuits times 20 amps per circuit times 120 volts equals 4,800 watts. Thirdly, calculate the laundry load for each dwelling unit. According to the NEC, each dwelling unit must have at least 1 20-amp laundry circuit. Therefore, the laundry load for each dwelling unit is 1 circuit times 20 amps per circuit times 120 volts equals 2,400 watts. Fourthly, calculate the range load for each dwelling unit. According to Table 220.55 of the NEC, the demand factor for ranges depends on the number of ranges. For 12 ranges, the demand factor is 0.47. Assuming that each range has a rating of 12 kilowatts, The range load for each dwelling unit is 12 kilowatts times 0.47 equals 5.64 kilowatts or 5,640 watts. Fifthly, calculate the other appliance loads for each dwelling unit. This includes the refrigerator, dishwasher, clothes washer, and electric dryer. Assuming that each appliance has the following ratings: refrigerator 600 watts, dishwasher 1200 watts, clothes washer 800 watts, electric dryer 5000 watts. The total other appliance load for each dwelling unit is 600 watts plus 1200 watts plus 800 watts plus 5000 watts equals 7600 watts. Sixthly, calculate the total load for each dwelling unit. The total load for each dwelling unit is 3000 watts plus 4800 watts plus 2400 watts plus 5640 watts plus 7600 watts equals 23,440 watts. Seventhly, apply a demand factor to the total load for each dwelling unit. According to table 220.42 of the NEC, the demand factor for dwelling units depends on the number of units. For 12 units, the demand factor is 0.38. Therefore, the demand load for each dwelling unit is 23,440 watts times 0.38 equals 8,907.2 watts. Eighthly, calculate the total demand load for the building. The total demand load for the building is 8,907.2 watts per unit times 12 units equals 106,886.4 watts. Ninthly, calculate the load for the common area. Assuming that the common area has a lighting load of 1000 watts and a receptacle load of 500 watts, the total load for the common area is 1000 watts plus 500 watts equals 1500 watts. Tenthly, add the common area load to the total demand load for the building. The total load for the building is 106,886.4 watts plus 1500 watts equals 108,386.4 watts. 11thly, convert the total load to amps. Assuming a 208/120 volt three-phase service, the total load in amps is 108,386.4 watts divided by 208 volts divided by the square root of 3 equals 301.2 amps. 12thly, apply the 1.25 factor for continuous loads. Assuming that the common area lighting is a continuous load, the load must be increased by 25%. The continuous load is 1000 watts times 0.25 equals 250 watts. The total load with the continuous load is 108,386.4 watts plus 250 watts equals 108,636.4 watts. The total load in amps with a continuous load is 108,636.4 watts divided by 208 volts divided by the square root of 3 equals 301.9 amps. Therefore, the minimum required service size for this building is 302 amps. It would be prudent to install a 400 amp service to accommodate any future expansion or changes in occupancy. Remember to consult with a qualified electrical engineer or electrician to ensure that the electrical service is properly sized and installed.